Hey there everybody, welcome to our first video for this unit where we're going to learn all about the mole. And this is truly a momentous occasion. I don't know if you have any friends or siblings that have enjoyed chemistry before, and if you ask them, I'm sure they will look back very fondly on their time and learning about the mole, and I'm sure you will too. So the mole is one of these foundational concepts that is going to be really important for us to understand if we're going to move forward in chemistry at all. And because it's so foundational, at first it might seem a little strange. Like, what is the mole? What is it all about? I assure you that with time, we'll make peace with the mole and it will be your friend as well. So before we start talking about the mole, let's just talk a little bit about matter. So we know that if you have a chunk of matter, you can find its mass. And the mass is really just the amount of matter in an object. So if you have a 1 kilogram potato, that is 1 kilogram because if you add up all the little bits of matter that make up that potato, they will add up to 1 kilogram worth of stuff. Now, if you compare that to atomic mass, which is you want to talk about the mass of a single atom, the atomic mass is really just due to two things. So atomic mass is equal to the number of protons plus the number of neutrons. And we'll use this little symbol for P plus for protons and N with a 0 for neutrons. Now, a reminder that protons and neutrons have essentially the same mass and they're located in the nucleus. We sometimes call them nucleons because they live in the nucleus. And it turns out they don't have exactly the same mass, but it's very, very close. And so we can say that if we have an atom and it has a mass of 50, that's because it has some combination of protons and neutrons that add up to 50. Now, also a reminder, you might say, well, what about the electrons? So electrons are there, and they also are made of matter, but they're really, really small. So just a reminder that electrons have approximately 1/2000th the mass of a proton or neutron. So yes, electrons are matter and yes, they have mass, but it's so much smaller. They're so much smaller that we don't really factor it in. We don't count it. Now, a couple of reminders here about atoms, and these are not big surprises. When we talk about atoms, atoms are extremely small. They're almost incomprehensibly small, okay? But since they are so small, and they are what make up all the matter around us, they are very, very numerous. There are a lot of them. And so if we want to do some chemistry, which is we want to react different chemicals together, we can't talk about what happens. What happens when one atom of this reacts with one atom of that? It doesn't really make sense. When we react things together, there are going to be huge groups of atoms reacting with other huge groups of atoms, okay? Now, when we talk about individual atoms, we can talk about something called atomic mass. And the atomic mass is measured in atomic mass units, which is a very creative name. Chemists are very creative. And so that is abbreviated as AMU. So 1 AMU is simply equal to the mass of a proton or of a neutron, because like we said, they have essentially the same mass. So just as a quick example here, I've got 3 different atoms. I've got hydrogen, then I've got a couple of heliums. Well, this hydrogen, it has 1 proton located in its nucleus. So this would have a mass of 1 AMU. The electron spinning around the outside doesn't really affect things. This second atom, this helium, has 2 protons, and remember, 2 protons means it's helium. That's all you need to know about it in order to know that it's helium. It's 2 protons. But it also has 1 neutron, and so that would have a total mass of 3 AMU. And then this last atom here has 2 protons and 2 neutrons for a total mass of 4 AMU. So I just want to point out a couple of things here. So these 2 atoms have the same number of protons. If they have the same number of protons, then they are the same element. Full stop. Nothing else matters. Neutrons, electrons, who cares? 2 protons means helium, end of story. But they do, as you notice, have a different number of neutrons. So they have a different mass because they have different numbers of neutrons. And so because of that, they have a different mass. They're still going to react really similarly, because they're still both helium, but they weigh slightly different amounts. And the term we have for that is isotopes. So two atoms of the same element that actually have different masses, we just call those isotopes. Now, back to the real chemistry. It turns out we don't, as chemists, really care too much often about the atomic mass of individual atoms because we are never reacting individual atoms. Imagine you had to bake a cake and I said, hey, can you go and find for me 92 trillion grains of flour because I need to bake this cake? Well, that would take you a very long time to measure it out. If instead I just said, hey, can you go get me 1 cup of flour? Well, that's very easy to measure. And I'm not asking you to measure the individual grains of flour in that cup because that would be ridiculously hard to do. And by the same token, we're not going to ask you to measure out the individual atoms in a sample of a chemical because that would be too tough. So instead, we use this idea of the mole. And so a mole is just a number of things. So it could be atoms or molecules or really anything at all. Think of it like the word dozen. If I ask you to get me a dozen eggs, you know that I'm asking you to get exactly 12 eggs, not 15 or 72. A dozen is 12. And by the same token, 1 mole of something is going to be Avogadro's number of that thing. And so Avogadro's number is defined as this right here, 6.022141179 times 10 to the 23 things. We will just sort of approximate 1 mole as being 6.02 times 10 to the 23 items, whatever they are. Atoms, molecules, eggs, it doesn't matter. And so the thing to consider is that this is a very, very large number. Times 10 to the 23, that's 6 with like 22 zeros coming after it. That's a lot of, that's a really big number, okay? So 1 mole is just going to be 6.02 times 10 to the 23 of anything. And one thing to consider about this is that is a very, very big number. And the reason it has to be such a big number is because atoms themselves are so tiny. It wouldn't make sense to measure out individual atoms. It wouldn't make sense to measure them out by the 100 or by the 1,000 or even the billion. We need a really, really big number to measure out these atoms with, okay? Now the abbreviation for mole, it's a good one. It's MOL. See that? Abbreviated it by 1 whole letter. So much simpler. MOL is not the same as molecules. MOL is definitely mole, and it stands for this many things. So let's see how we could start to use that in some examples. So the first question there is how many lithium atoms are in 3.2 moles of lithium? So I'm going to start this off by asking a question. How many lithium atoms? So that's my first question. How many lithium atoms is equal to, and then I'm going to pull some information out of the question there, which is 3.2 moles of lithium. How many atoms would I find in 3.2 moles? Well, what we're going to do with this, and this may seem like an overcomplication at first, but there is a reason for it, is we're going to use a system called unit conversion, which is I'm just going to multiply this number by some ratio which will allow me to get the answer I'm looking for. Now, the only ratio we have right now, although we'll learn many others, is we have this one right here, this Avogadro's number. And so we can use that to our advantage. So whenever we multiply by a conversion factor, we can do it one way or the other. I can either multiply by Avogadro's number over 1 mole, or I could flip that around and multiply by 1 mole over Avogadro's number. Since I have moles here on top, I'm going to make sure that moles end up on bottom of my conversion factor, and I'm going to multiply it by 6.02 times 10 to the 23 atoms of lithium over 1 mole. A reminder as well that Avogadro's number can count anything. In this case, we're counting atoms. Maybe some other time we'll count ions or electrons or molecules. It doesn't matter. And so when I do this, I can see that moles here cancel out. And the units I'm left with are atoms of lithium, which is what I wanted the whole time. So when I put this in my calculator, I get an answer that's right around 1.9 times 10 to the 24 atoms of lithium. And that's my final answer. Okay, so let's look at another example here. So I've got How many oxygen atoms are in 7.8 moles of oxygen gas? So first thing is to identify the question. How many oxygen atoms? So how many atoms of oxygen is equal to 7.8 moles oxygen gas? 7.8 moles of oxygen gas. Now, be careful here because oxygen is one of those funny elements that on its own is going to always form diatomic molecules. So you never find oxygen just floating around by itself. You will always find it in the form O2, and that's going to matter. So my first step is to multiply it by a conversion factor. Again, I've got Avogadro's number. I can multiply this by Avogadro's number, 6.02 times 10 to the 23 molecules of O2 over 1 mole. And we can see that the moles here are going to cancel out. But I'm not done because I don't want to know how many molecules of O2 there are. I want to know how many individual oxygen atoms there are. So I'm going to have to multiply this by another conversion factor, and you're going to have to come up with this one on your own. You're going to have to look at it and say, well, hold on a second. There are 2 atoms of oxygen for every 1 molecule of O2. And you can see here that the unit molecule of O2 cancels out, and I'm left with atoms of oxygen. And when I calculate this whole answer, I get right around 9.4 times 10 to the 24 atoms of oxygen. And that is my final answer. All right, so there's a few more practice problems here. I want you to try these. I want you to hit pause on the video, go give these a try, and then come back and see how you did on the answers, okay? So definitely pause the video and go try them. And now that you've definitely paused the video, and now you're definitely unpausing the video after doing all of them, here are the answers, okay? So I'll just scroll through these kind of quickly so you can see all the different answers and enjoy all the wonderful multicolored chemistry that you have before you. Aren't you lucky? Okay? So that is it for our first video on the mole.